Hi everyone, thanks for joining us today. We have another webinar in our series of webinars from academy to academy. Today we won't be talking just about our products or technologies or what's not. Today our colleagues, partners, and friends from universities, colleges, and research centers will share their experience in drone-based remote sensing. How they use magnetometers, echo sounders, GPRs, and all other sensors to advance their research, to get better data, to find new insights, and to make breakthroughs. Today we will cover all the areas or forces, so to say. We have water for bathymetry, and Tyles Sowden, technologist from Mohawk College in Canada, will share their success story. Then Jamie Davis from UAS Center, Ohio, he'll share their experience with drone-based archaeology. And Michel from Université du Québec will share their experience in glaciology with drone-based GPRs. A bit of organizational things and housekeeping. If you have any questions, ideas, things to discuss, please use Q&A section. If you want to tell something or to ask something, you can raise your hand and I'll give you this opportunity. Because we don't expect many people today, I think we can make our round table like a conversation. We have 1 hour. We'll be trying to be on time and keep this timing, but be ready to spend a bit more time today. Tyler, you're the first today. The floor is yours. Thank you for being here. That's a real pleasure and seeing you all here. And I'm excited to hear your story.
Thanks for having me. Just going to get my screen sharing before I start. Today, I'm going to be focusing specifically on the sonar bathymetry stuff that we were doing with the city of Hamilton, if anybody was unaware. It was a rather large project, so I am going to try to keep it down to the overall value add rather than a deep technical dive. If anybody wants to discuss a bit more technical stuff, my contact info and all my colleagues' contact info are going to be at the end of the presentation. Don't hesitate to reach out if you're looking to integrate something like this into whatever organization you guys are part of. So before we get started, Mohawk College, as mentioned, we're here in Hamilton, Ontario. Within Mohawk College, we have what's called IdeaWorks, which is kind of our hub for innovation. They really look after the administrative grant and partnership stuff so that the researchers can focus more so on the research and the doing. Within that, we have URSIC, so the Unmanned Remote Sensing Innovation Center. That's us. We focus on remote sensing. We get labeled as the drone guys quite often, but we're far more than just drones. It's really about the payloads mounted to the drone, to the rover, or to a boat solution as well, which is what we're starting to get into. For this project specifically, just overview of City of Hamilton's kind of watershed. They're pretty complex. There's a large escarpment here, which has hard surfaces, which result in natural runoff rather than water absorbing into the ground. They have over 60 municipal stormwater ponds. Those are just the wet ponds. And those are mostly on top of the escarpment to stop it from really causing erosion on its way down the escarpment. So they also have a lot of urbanization happening, so they have an increased need for capacity of their existing ponds and increased ponds going online. Their team's not getting much bigger, so they really need to find more efficient ways of doing things, stormwater, sewer, everything as a whole. This project specifically, just quick stats about it, it focused on those stormwater ponds, specifically how to survey them. We broke it up over 2 years. Efficacy kind of happened that second year, more exploratory stuff happened in that first year. 12 students, and we surveyed almost a quarter of their total ponds, really getting as much data as we could so we could get them proper insights on the efficacy of that unit. And the the city of Hamilton, just spoiler alert, they enjoyed the solution so much that they're looking at integrating sonar into their workflows, whether that's adopting in-house or tendering it. They're going to start doing it soon. So before we get into the actual project, let's just quickly go over for anybody that isn't familiar with stormwater ponds. So you might just see them alongside, a highway and think the highway was built around it, or maybe it's just the pond that you walk your dog around in your subdivision. The fact of the matter is they are not natural, as much as your real estate lists it for waterfront property. If you get one of those neighboring properties, they're purpose-built civil infrastructure. They're man-made, and they have to be maintained. They're there for a purpose of catching sediment and catching pollutants to stop it from going into the actual natural watersheds. So if you see on the side there, the pollutants, there's going to be brake dust, tire rubber coming off of the street as the stormwater washes it in. These ponds are here to stop it. And if they're not holding the volume, it pretty much negates the entire purpose of the pond. So just quickly a diagram, how they work. The inlet there on the left side, it comes in, that forebay is going to catch most of the debris, the litter, all the sediment. Some of it gets into the rest of the pond, but the entire pond itself is there to retain that water and let it either boil off, sink to the bottom, or the little that's left does go out the outlet. The best solution to pollution is dilution. So it's small amounts that end up going into the natural water course that are kind of negated just by the quantity. So why survey them? Here in Ontario, the ministry sets out strict parameters in what's called an ECA, environmental compliance approval. The municipality has to follow those parameters. It's on them to monitor and maintain them to meet kind of within tolerance of those parameters. And when they're outside of those parameters, the ponds have to be dredged. Next slide goes over what dredging is. Dredging is pretty involved. They have to drain the pond. The pond goes offline, and they have to scrape the sediment, pump it into a big pit, make sure all the water drains out, and then that sediment has to be remediated. So you can imagine it's a pretty costly endeavor to go on. Do it too often and you're wasting taxpayer money and for a maintenance activity that doesn't even need to exist. You're also destroying a little bit of a micro ecosystem. As much as they are man-made, they get dredged every maybe 7 to 20 years, depending on the pond. And life does, you'll see birds nesting in the reeds and stuff around there. So that's happening as well. The flip side is you dredge them too late and you're negating the entire purpose of the pond. All that sediment is going into the watershed. All the pollutants are also going into natural rivers, streams, lakes. We're here in Ontario, in Hamilton, we're on Lake Ontario. So you really want to make sure you're on top of stuff, because those things that I mentioned before don't sound really good for fish, wildlife, and habitat. So really getting that just right sweet spot of when to perform maintenance activities comes down to how accurately you can measure them. Right now, traditionally, they're using one of 3 traditional methods. So GNSS, total stations, or leveling rod. Those are items that have been, purpose-built for land surveying, and we're making do with them for bathymetry right now. So with a prism pole or a GNSS rod, they usually have to put an extension on. The rods only go to 2 meters. So they have to make a 3 to 4 meter rod. And then they have to navigate in an unpowered vessel, kind of drifting around, whether it be a dinghy, john boat, canoe, or if it's shallow enough, which some ponds are, you can get away with waders, but then you're rummaging around through the pollutants in the sediment. So the issues with the traditional methods, which I'll touch on later, it's tedious to navigate. There's limited data points, and it takes a long time to deploy the boat and get those limited data points, and repeatability can be hard. You'll see here, this is traditionally how currently how a traditional bathymetric survey would go. So they'll do a bunch of transects every couple meter spacing, and then one line down the middle, and they use that limited data with the profiles at each transect in the middle line to basically do a rough calculation of the volume. They're usually erring on the side of caution, because if they're being too liberal with it rather than too conservative, they're going over the compliance, and that could have some penalties. So that's where we came in with this project. Phase 1 started in 2022. And like I said, we did 14, 15 ponds. And we're really trying to find a solution to each one of those problems. So bathymetry has existed since World War II. It's not really new, but it's always been expensive. And really, it only solved the data problem where you're retooling it, so you're using sonar, right? You're still deploying it on a boat, and with that boat came the other inefficiencies I talked about. So we're looking to solve each one of those problems. I'm going to get right into the data for kind of the phase 1 stuff. The left side is our raw soundings, so that's, you can kind of see the flight line. I'm just going to get my highlighter out. So right here was the inlet for this pond, and then it goes over a rock berm here, and then it has to go do this pond, and then there was kind of a cable dam right there, and then it goes into the last pond before it goes into the outlet and eventually leaves the facility. Traditional methods, you would have to do 3 boat deployments. So, you know, if you're portaging like just over the rocks, it's not too bad, but the drone was able to just hop over that berm. For the transect spacing, you'll see it's a lot better than what they were getting traditionally. So each one of these lines is about 2-meter spacing. We kind of clustered them tighter, closer to the banks. On top of this, we also did edge of water surveys with the GNSS rod, so we can get the water level at that day. The bathymetry software will take kind of these edge data recordings and really trace them out to wherever the water lies that day. These maps were also collected the same day using photogrammetry. So if for whatever reason we weren't able to collect edge of water, there was some property owners that definitely didn't like us being on their property or the easement of their property. So sometimes it's easier to just put a drone up and not really have that interaction with a property owner. So we're able to get all the way around. We're able to get all of our data at 2-meter spacings. We did start adding kind of middle lines as well, getting really as much data as we can. All of that data goes into HydroMagic, and then HydroMagic makes what you see on the right. So the process depth matrix, kind of like a heat map for depth. I just do want to stress that the equivalent to doing this terrestrially is if I told you to survey an area and then blindfolded you, you really don't know what's under the water. So getting as much data as you can really helps. This pond took about an hour to collect once the flight plan was done and everything. And you can see it's got pretty well everything except that berm, which is pretty negligible for volumetrics. It's just a shallow amount of water that's flowing into the next pond. Another pond we did, and this one has some cool highlights. So this pond is up in Ancaster, so it's right on the escarpment brow. Because of that, limestone was pretty shallow. So my understanding is that they made these ponds large and shallow so that they didn't have to dig down deep. So these would have took a long time, and they have some complicated geometry. So doing it traditionally would have been, you know, transect line, and really getting limited data all the way around, and it would have took hours. So water comes in through right here, kind of on this S-shaped pond right there, goes all the way through. There's a culvert here, and it goes into this next pond to get retained into these 2 ponds, these 2 cells. So if you look over at the depth matrix, you'll see kind of good data all across this pond. Keep in mind there was kind of shallow weeds as well, so you'll see some clusters of weeds. And then when it enters in through that culvert, you actually see this micro pool here. It's pretty deep. Since water's rushing so fast, sediment didn't really accumulate there. If you were to do this with the traditional method, without sonar, if you were able to just, you know, take your GNSS receiver and dip it in, maybe you did a transect here and a transect here. What it's going to do is it's going to find that, and your volumetric is going to do a line that goes from here all the way to here, kind of as a straight arc. That is going to kind of give you volumetrics that don't really exist, right? So that depth, you know, exists here, and it would be tracing it out, but really it's a bit smaller and a bit deeper. So we're able to find micro pools and account for that. Also, traditionally, you might just miss that completely. If that micro pool is right there, and you do your transect line just on the brow of it and on the next one, you have volume that you aren't even accounting for. Over here, you have the opposite. So you'll see on the raw soundings, there's a distinct lack of data on this pond. This one was shallow and it was below the sensors. I think it's a 0.3 of a meter, so it's 30 centimeters, 30 or 20. So this area didn't get many soundings. Alternatively, you might have got them with a traditional method, but it's really not holding that much water. So what it does is it takes the data that it does get kind of around that area, and it traces out a line of best fit, kind of a straight arc going over to the water edge survey that we did. So all in all, just going over kind of the problems that we touched on before, tedious to navigate, that's solved distinctly by the drone. If you had a unmanned boat or a manned boat, it still isn't able to get over those berms. You still have to kind of bushwhack to get to the pond itself, right? A lot of these are surrounded by invasive Phragmites, which is another discussion. But you're able to get access to the ponds incredibly easy. You're able to hop over berms and dams that exist. That limited data is solved by just the fact that SONAR was able to get us, 100 times more data points. I didn't really show it, but along those lines that the sonar is collecting, it's collecting at, I think it's 10 hertz. So it's taking a shot every 10 milliseconds. So it's it almost looks like pointillism. It may have looked like a straight line, but it's a bunch of data all along that line. So it really gives you an accurate kind of cross-sectional area of that pond. And then you're able to space those transects 2 meters apart or even 1 meter apart if the pond demands it. And then you have long deployment time. That was relatively the same the first time out to the pond because we had to get out, look around the pond, figure out, what weed stands we had to avoid and overhanging trees and do our flight plan. But these ponds get surveyed every year. So what's nice is you can go out the next year, press play on the flight plan, and it's just going to go and take probably half the amount of time. It's already planned for. And like I said, some of the ponds that would have took 3-4 hours traditionally took an hour or less. The drone does have to move decently slow just to stop kind of the deviation between the drone and the cable angle. But it's still far, far faster than traditional methods, and you're getting 10 times, 100 times more data. And then that last problem, the repeatability can be hard. That's really what City of Hamilton wanted was less guesswork. They wanted to be able to go out, take the same measurements year over year, and kind of negate some of the guesswork that went on. Because even for a seasoned surveyor, right, you're still looking at an engineering drawing and inferring from that and going out and collecting that data. You're doing it blindfolded. UGCS is able to get rid of that, and it's also able to go out the next year, do the exact same mission plan, and it solves kind of the repeatability aspect of the issue there. Phase 2, so this took place over 2023 to 2024. It was all about efficacy. City of Hamilton really, really, really liked the data we were getting. But in order to start tendering it and using it as a certified means of managing their ponds, they really needed some efficacy trials and some comparative analysis done on it. Luckily, in the 2024 year, they had 3 ponds that were undergoing full dredging. So remember what that means. They got to drain them, scrape the bottom, and then refill them. So we took this as an opportunity to do a bit of comparative analysis between our methods and more traditional methods, not traditional sonar or traditional bathymetry, sorry. But since they're drained, we can actually use land surveying tools. So us specifically, we coordinated with the dredging contractor before they started any work. About the week before, we would go out, and as the ponds were wet, we would go and run a drone-mounted sonar run. And then as the contractor was draining it, we went and did photogrammetry and LiDAR. We were able to compare both of those and the volumetrics kind of that both of those availed. And then the contractor dredged it, but didn't start diverting water back into it. We went out and did another photogrammetry and LiDAR run. And then once water was back in, we did sonar. So really, we have kind of 2 clusters there of data that we can compare to make sure they're meeting spec. On top of that, the contractor goes out, and as soon as they dredge the pond, they do a GNSS survey. So we had that data as well. So a traditional kind of boots on the ground approach, we had that data as well. The kind of findings there on the next slide. First, sorry, I'll cover the the data sources that we use. So for our calculations for the drained ponds, like the dewatered ponds, photogrammetry we did on a Mavic 3, and we did all the stitching and photogrammetry processing in Pix4D and did volumetrics in Pix4D. For the LiDAR, we used our Scout 32. It's a Phoenix LiDAR solution. Flew the ponds, it was only one line, and then processed that data, and we were able to bring that into Civil 3D, register it as a topo surface, and do volumetrics in Civil 3D. So the findings on one of the 3 ponds, here's that first one. You'll see there's about a 6 to 8% difference between all 3. And if you look on the right in that kind of background there, you'll see there's a lot of weeds. Our suspect for that deviation was the weeds. And again, the alternative traditionally is you're just not going to get that data. Photogrammetry would register those weeds as kind of a big cluster. LiDAR is able to get through it a bit more. That's why you see it thinks there's a bit more volume in there. There's standing weeds, and then there was like lily pads and floating pearl weeds. After they dredge the pond, though, you see those numbers go back in, and it's a really tight cluster where they're only separated by tens of meters cubed. So there's the heat map. So I'll just leave that up. And worth mentioning, you'll see kind of there's a flat line here, and then there's kind of a coast here. The pond water volumes were completely different at the times of surveying, but they get calculated as what's called permanent pool. So that ECA approval that we talked about, it calls out a elevation at permanent pool that you basically calculate just to make sure you're comparing year over year properly. On 2 of the 3 that we did, same thing. We were getting really tight stuff. Sonar was usually closer to the LiDAR, which we trusted the LiDAR more. Photogrammetry is gonna be a bit less accurate than our LiDAR solution. And then after the pond was dredged, we've had the same findings. After the pond was dredged, this pond we did get the contractor data for. They had a volume of 730. So all of our stuff was pretty close, and I don't want to gloat, but I think we were getting more data points than they were traditionally. So the gains, both for the city and for Mohawk, the city got all of 14 ponds surveyed, and they didn't just get calculated volumetrics of the ponds. They got depth matrices, they got the raw sounding so they could calculate, manual takeoffs if they needed to. They got the LiDAR point clouds, and they got the photogrammetry maps. They got guided exploration of that technology. They hadn't adopted sonar in any kind of capacity yet, at least in the water division of the city. So we were able to help them kind of de-risk that technology and make it a bit easier for them to adopt. On top of that, they got to de-risk the sonar and really get a proper efficacy test done with kind of our fleet of drones here at Mohawk. And validation of the sonar collection methodology. So they came out, they were present at kind of all the collection times, really observing how things were done, and they really got to see how much easier of a solution it was. And then they got knowledge transfer and documentation. So our students mostly did the processing, and as they were doing the processing, we got them to put step-by-step guides together, video tutorials. We as faculty and staff did the reporting and the presentations of the findings. And then we were also able to help them write tender specs. So if the city wasn't able to adopt anything in-house, they at least have a means of tendering out for it, because like I said, the data was leaps and bounds ahead of how they usually do it. And they think it's really going to stop them from dredging too soon. What did the college gain? So we got real life experiences brought into the classroom. Currently, we're showcasing this methodology in our surveying courses. Our municipal service courses are also going to start getting live demonstrations of bathymetry. Specifically, we're going to bring out the drone mounted sonar because we think it is the best. We do have a boat, but the ponds, we're also undergoing kind of a invasive invasive weed kind of problem here in Canada. So the ponds are usually gunked up, and they're there to collect litter too. So a lot of the ponds we put our boat solution in, the propellers just got jammed with debris. One pond, you know, you thought the pond was on a farm, it was close to a farm, and it was free of debris and litter from maybe like a highway pond would have. But we got a hay bale strapping stuck in the propeller, which put us out of service for a couple weeks. Experience and opportunities were given to students. So like I said, it was completely processed from students. So we had 12 students on the project, all doing data processing. We had a few pilot students. They didn't get to fly, you know, the big toys, but we let them do the photogrammetry mapping and some of the videography. And then we had 2 students do capstone projects based on this project. So those are those projects that they're going to go to a technical board and so that they can get their affiliated with an organization for civil engineering. Future ready educators. So this one to me is pretty important. As educators, we shouldn't just be teaching how things were always done. We should really be helping lead the bleeding edge rather than kind of just adapting to when it does get adapted into industry. And we should be doing that with students. So if you don't bring students along and you exist in kind of a silo chamber, then really it's suboptimal. These students are going to be the future of our industry. And if you can bring them along at the same time that you're learning a new solution and they can learn a new solution, they leave excited and ready to create change because they already did it. And then I'm going to leave our contact info. As I said, this is just kind of a broad overview of the project. If you want any technical information, feel free to reach out or ask it in the question period at the end. But I hope that covered most of our project. And yeah, I'll give it back to Alexi.
Thank you, Tyler. That's, I would say, exciting and really great example of how college and universities and academics in general can collaborate with governmental agencies, municipalities, and help them to be more efficient, so to say. Quick question from Errol Williamson about GNSS ground stations. Did you use one GNSS station or multiple stations?
So for if he's asking for like RTK correction or corrections in general, we used network RTK, multiple different types of network RTK. We have a few different ones we can choose from, but all the RTK and corrections were done through a network service rather than setting up a ground station.
Okay, thank you. And I suggest we'll discuss all other questions after all presentations. Jamie, please, your turn. Take the mic and share us what we can do with drones in archaeology.
All right, so hello everyone. So my name is Jamie Davis of the Ohio UAS Center. We are part of the Ohio Department of Transportation, but we are also a shared resource for other state agencies within Ohio, like the Department of Natural Resources, EPA, Department of Health, and a few others. And because of that, we get to try a lot of things that typically aren't part of transportation or what you would think of as transportation oriented. So today I'm going to talk about our magnetometers on UAS. So we started the magnetometers and UAS back in 2019 with a partnership with the Department of Natural Resources, looking for the orphaned wells that are in Ohio. There was a infrastructure bill passed by the U.S. government a few years ago, and part of the money set aside in that bill was to find all of the orphaned wells throughout the country. And for whatever reason, Ohio was one of the first states to get the money to do that. So this is a picture in Grand Lake, St. Mary's. This is supposedly the first offshore drilling in the world. And there are orphaned wells all over the state. And we're using a magnetometer to find them. So that's our Skyfront Perimeter 8 flying over Grand Lake with a mag arrow dangling below it. And these are the results. So ended up using the mag arrow on about half of the lake. And then we got our hands on a Census R3 and just strapped it straight to the front legs of the Perimeter 8 to see how it would work. And it works just fine. So we ended up doing about the other half of the lake with the Census R3. And then we did have a bit of an issue with our Perimeter 8, and that was down for a while. So we ended up having to use an M600 to do along the shorelines. I can tell you that the Perimeter 8 will fly for, we were getting flight times of up to 2.5 hours with the Census, with the R3 strapped on. It's about twice, you can cover about twice the area with the Perimeter 8 as you can with the 600 and the amount of time. But what we're really talking about here is the low altitude magnetometry. So we actually started doing low altitude stuff. We have an SPH GPR that is the first thing that we got. So we ended up using the Sky Hub with the radar altimeter on an M600. And then we started working with the Department of Health to do radiation detection. So basically you move the GPR and put the radiation detector under the drone. It's the same process. And then we had a situation come up a couple years ago, and this is in Newark, Ohio. This is the Newark Earthworks. This is a newly minted World Heritage Site. It was added to the list just last year. So it's the largest earthen enclosure site in the world. Each one of those large circles are 1,061 feet or so in diameter, so 312 or 15 meters or whatever. Our interest was these two parallel walls that run off the octagon to the southwest. There's historic documents stating that these two parallel walls go for at least 12 miles. Some people think they go as much as 50 miles to another grouping of these prehistoric earthworks near Chillicothe, Ohio. But we had a situation, so over here is what's kind of left of the earthworks. The octagon is now part of a golf course, kind of saved it, I guess, the large circles here. And then there were two sections of these parallel walls that were known to exist down here. And then this red outline was a proposed development that was going to go exactly where these parallel walls were. And at the time, it wasn't really sure if anything still existed in the agricultural field or not. So Ohio has statewide LIDAR. In 2006, was collected at 3-meter resolution. So these, what are called the Van Voorhees walls, were known from that LIDAR. But then in 2020, Ohio got 1-foot LIDAR for this site. And we were able to see that the walls still exist, just barely on the surface in the field. So then the question was, can we try magnetometer? The ODOT's archaeologists got involved. They are learning. They have a Bardington handheld magnetometer. They were asked if they could do magnetometry on this section of the wall to see what still shows up in the mag. They just came to the conclusion that it was too big of an area for them to do by hand, and they knew that we had a magnetometer on a drone, so they wanted to see if we can try the drone magnetometer and see what would happen. I said, I have no idea what's going to happen here. I'm used to flying at 100 to 200 feet in the air and looking for giant wells. I'm not sure what we're going to see if we fly it as close to the ground as we can. So we ended up doing about 10 acres worth of area. As you can see, we mostly got, these are pipelines, existing pipelines through here. And if I zoom in, we do have, the prehistoric walls do show up in the mag. Now, without the LIDAR and seeing them in the LIDAR, I'm not sure I would have picked that out as being the walls. but this linear feature goes right over top of the LiDAR walls, and we get it in the south as well. The northern section is blown out by this pipeline. So this was our first attempt at it. This was using an R3 with the M600, set it up so that the R3 ended up being roughly 50 centimeters off the ground as it was collecting data. Tried to get it at about 1 meter spacing. So there's two sensors on the R3, they're 1 meters apart. So we shot for the 1 meter spacing. And we were able to get the earthwork. And then looking at the data, we started to see that some other features were showing up, some anomalies, some probably iron objects, but there was definitely some other things in here that are kind of interesting, starting to make us think that we can get even smaller features, prehistoric features. So we had a situation, this is the Ohio River is down here, and one of the district headquarters they want to build a district headquarter in this field, which is right by the Ohio River. So there could literally be anything prehistorically in this field, anything anywhere from a prehistoric village to, as it turns out, not much at all in there. But there was a historic site here as well. So we tried it again with the R3 on the 600. All of this noisy stuff here is where the historic site was sitting. But we can definitely start to see there's other anomalies showing up. Then we ran into a problem as I was processing the data. I noticed that the magnetometer GPS, and then I had an EMLID M2 writing on top, and we were getting network corrections to the M2. I noticed that they weren't lining up, as I wasn't expecting them to line up, but I wasn't expecting a uniform shift as we're seeing here. I was kind of expecting the GPS from the R3 to kind of be all over, kind of erratic. It didn't seem to be the case. So then I was kind of in my mind thinking, well, which data set should I trust here? So we ended up doing hand mag with the Bardington. Ended up that the M2 with the network corrections ended up being correct. So I had confidence enough to go in. Oh, this is the hand mag here. We ended up doing 4 blocks with the Bardington, and as you can see, so we do know there's issues with this Bardington data. All the waviness. They're actually getting trained next week to try to deal with the waviness, but you can flip back and forth between the two. You can see that the anomalies showing up in the Bardington are showing up with the R3 pretty well. So at this point, we're pretty confident in the locations. Some of these anomalies look pretty good as being prehistoric pit features. So I picked out several, the soil probe. So we went out with the soil probe, and we were able to find prehistoric pit features that way. We did a pretty large area here, about 15 acres in size. I flew it. It took me 2 days. I was really dedicated. I could have done it all in 1 day with the magnetometer on the drone. And then we were so excited about the results that we got that we decided to upgrade our entire system. So we ended up, so that's Inspired Flight 1200A. That's the EMLID M2 antenna sticking up here. And this is a Census R4 strapped to the bottom. We have collected data on archaeology sites with this system. Turns out it's pretty noisy at this point. That's kind of reaching the limits of my knowledge. I'm not a geophysicist by trade, so I'm getting help by a geophysicist named Alex Corkum. But the center sensor, so the R4 has 5 sensors 50 centimeters apart. The center sensor is getting a lot of noise from the batteries and the drones. And so our next idea is we're gonna move the sensor to the back of the legs on the inspired flight to try to get a little bit more distance between the sensor and all of this mess. But initially, it's finding the anomalies. It's just cleaning up the data better. So I do have access to Terra Surveyor here at ODOT, so I'm working on using Terra Surveyor, and Alex is teaching me all the ins and outs of Terra Surveyor to clean the data better. But with this unit, we should be able to cover really large areas pretty quickly, so we can start thinking about landscape archaeology. Ohio has estimated 10,000 prehistoric mounds, probably several thousand of those earthworks, smaller earthworks, lots of circles in the 300-foot range throughout Ohio. Start using this for landscape archaeology for those type of things. That's our plan moving forward. And that's the end of my presentation.
Thank you, Jamie. Also, quick question from Bastian. How deep was the lake? The first one that you shown for mapping orphaned wells.
How did we do what?
The lake where you mapped orphaned wells.
How did we fly it? Do the
How deep it was? How deep was it?
So it's not very deep. It's probably at its deepest parts like 20 feet. Shallow. Most of it's in the 10 feet range. We're flying about 100 feet off the surface of the water. Can definitely detect the wells higher than that. We've done other projects where trees existed, and after hitting a few trees, I know that trees. I did LiDAR on a UAS LiDAR in an area. Trees can get up to like 170 feet tall in Ohio. So sometimes we have to have the mag at 200 feet, and we can still find the wells that high.
Thank you. Thank you, Jamie, for this amazing presentation. And it's now time to move to Michel.
So yeah, good morning, everybody. So it's still the morning here, but so I'm Michel Baraer from ETS. ETS is a engineering faculty of University of Quebec. So and what I'm going to present today is, of course, come from my lab, but would not exist without cooperation from my colleagues from McGill University and from the Ohio State University. So here we'll think that Ohio is the center of the world for drone-based geophysics, but because Jamie was in Ohio too, maybe it is the case. So what I'm going to talk to you about today is about, first of all, why do we do drone-based geophysics, and what is our goal? We are academics, so it means that our job is to do research for science and to try to answer with the technology some questions that remain unanswered in terms of how the Earth works, and especially in our case, the waters that come from the ice. How does that work, and can we predict what's going to happen with climate changes? So we study cryosphere, two study sites mainly. We have also other activities, but mainly we study snow hydrology in Quebec, and we study glacialized watershed, hydrology and hydrogeology in Canada, in Western Canada. Our work is field-based, and what I want to stress is that we try to follow a multi-method approach. What does that mean? So yes, we are going to talk about drones, we are going to talk about GPR, but we are not specialists in one of the technology. The process we study are quite complex, and it's clear that only one technology cannot help us to answer the question we study. So we have to use multi-method approach. So I just placed at the top of this slide the other method. I'm not going to talk about that, but we are using ground-based geophysics or geohydrophysics with ERT. This year we introduced seismic. GPR is what we're going to talk about, and we even have now surface nuclear magnetic resonance that we are testing it also. We use LiDARs, we use a lot of monitoring equipment that we leave on site, and also I think we have a good specialty in natural tracers. So we take samples and we try to find the signature of the origin of the water that we study. So all together has to be combined and to answer questions regarding drone-based geophysics. So we, year after year, I mean, we acquired more equipment. You see that there is quite some orange in this slide. So it means that we've been working with our colleague from SPH. I think started to work together in 2001 or something, 2021 or something like that. And so we first acquired B-static GPR 500 megahertz. Then we wanted to do some application on snow. So we discussed, hey, do you have something with higher frequency? And I think we did acquire the only prototype you made with 1.5 gigahertz. And that was mainly for snow hydrology. And then we moved to low frequency to go to see deeper in the ground and to locate the ice. So we have now different UAV. So we have the standard Mavics for even the 3T here for photogrammetry or thermic surveys. We have M300. We have our good old M600. And now our colleague from Ohio just acquired a hybrid drone, the Harris one. And we are today, my team and the Ohio team are trying to make adapt the low frequency GPR to this unit for mission we have this summer. Of course, we also have to invest in GNSS, whatever. And we have also other payload, like we use LiDAR for mapping what we study. So two sites, as I said, one is here for the winter, 1 hour drive from Quebec. We have an experimental watershed, and my contribution to this center is really snow hydrology. And in the winter now, at least once or twice a year, we go to the St. Elias Mountains to study glacial hydrology. Let's start with that one. So just a more precise map for you to know where we are. So we are here in southwest Yukon at the Alaskan border. We are in the St. Elias Mountains, and you have here a huge ice field that are considered as being in the subarctic region. And those regions play a huge role in terms of hydrology and regulated river flow, etc. But they have been understudied because they are remote. It's a park, so these conditions are not exactly easy to conduct this kind of research. And we especially focus on the specific spots here that you have the map on the right. I think I have a picture that explains it better. It's, we work in the context of climate changes that have a huge impact on cryosphere. So in other words, cryosphere is retreating extremely fast in those environments. And here you have two pictures, one from 2018 and the other one from 1947, when you see the visual changes in this region. And the point is that when the glaciers retreat, they leave some ice bodies behind that get buried. And these ice bodies, they play a very interesting role in hydrology. And in fact, it's so interesting that we don't even know exactly how it works. But we know that they help to channelize the water that come from the upper part of the watershed and connect it to a deeper aquifer. And this is a very interesting point because, this would be the hidden water sources that never show up at the surface. And we don't know to which aquifer they or to which water resource they contribute. So the point here is when you are there, you cannot drill. You just have to study what's in the ground using, tracers or geophysics and things like that. And that's where our work started with there. So here we had the experience of dealing with, the B-statics 500 and 1.5 gigahertz. And so the first things we had to do is to test it in those environments. The point is that you know, geophysics, you only get, you know, a radargram with a bunch of lines, things like that. It's extremely difficult to say, oh, here I see the debris ice interface, here I see the bedrock. You just see lines. So the point is that we had a concern with using a drone-based GPR to do that work, because when you do drone-based GPR, you have to know exactly what you measure. So when we study snow, we just do snow pits and say, oh, you have an ice layer here, and we made the link with radargram. Here, it's not possible. And that's the good part of the story, because then we approach Alexei and say, Alexei, we're very much interested in your LF product, but this is a monostatic antenna. And in order to qualify what we have in the ground, we need to do what we call CMP. It's a GPR method where you have two separate antennas and you move away from the center, and by that point you get extra information like the permittivity of the milieu you are studying. So, and that was a very good story, because Alexei came back with a proposal and say, yeah, we can do it. So here it's a system. So the main system is LF, but we had an extra antenna and the possibility to apply it from the ground and be static. And in fact, it works really well. And there is a paper from a student from Ohio State University who would say, hey, look, the combination of both allow us to not only detect different things, but also to qualify what we see. So say, yeah, because of the CMP we've been able to do at a certain point, at just one point, for the entire transect, now we are able to differentiate between debris and ice. So we are able to map buried ice. So this is a work at 2 years from now. And the point is that now we are using that method to answer really our research questions. So also using the ARIS drone is also to make sure that we can cover, large area, much larger than a couple of transects, because these valleys are square kilometers large. So that's what we try to do this year, and hopefully at least the techniques works, and the way to treat the data works, and the CMP aspect works also. Let's move back to Quebec. So here it was I didn't do it in the right order, because we started our experience with the GPR, more with snow hydrology. Same kind of question. Climate change, snow cover we get less snow year after year, but also we get more and more variation, mild episodes, and freezing, refreezing, melting, or thawing events. So this creates more or some stratification of your snow. And the problem is that this when you produce ice lengths, for example, of ice layers due to those episodes, you create an impermeable layer in your snow pits. That makes that the water, the next rain and snow event that will happen, makes that this water might go straight to the hydrology, the drainage system onto the river, and create winter flood that it was in the past. So there was a concern here, and say, okay, let's try to use this GPR, because here it was the main aspect was the fact that it was non-destructive, because if it's drone based, you can fly during the whole winter over the same area, and you have repeat measurement without any with very limited impact on what you study. So okay, so that's just what I said. So just to explain the why we need this kind of tool in hydrology is really because we have this continuous interaction between meteorology, the structure of the snowpack, and the water that goes through it. So it's a bit more complicated, because so far we have been using what most of the people use with GPR is what we call the TWT, two-way travel time. We just measure the time that the signal goes through your different milieu, and you study. But when we speak about snow, the problem is that there is huge difference between wet snow and dry snow. And we know that the application of GPR with dry snow is good and allow you to measure the density of your snowpack. But when it's wet, it's much more complicated. So we say, okay, let's do it. And so we say, let's use other information from here's the radargram. We used, of course, the two-way travel time, but we used also what we call central frequency attenuation, the fact that the frequency changes from, the signals that come back to your antenna. So, and we use the fact that this change in frequency is affected by the water content. But you have also another very interesting point, that's the amplitude of the signals that come back. So let's try to find a way to develop a method that allow us to study snow hydrology in both wet and dry condition. So we typical radargrams, you had some kinds that are really simple, but we had different transects here, and we flew once a week over those transects repeatedly to see the evolution and to see if we could characterize the water content of the snowpack. So here is what happened with the results. Here at the bottom, you have two superimposed set of data here. The large one is just photogrammetric surveys that we did every week, also just to measure the snow depths in space and snow variation. And then in blue here, you have the estimation of the liquid water content. Here again, repetitively over the same surface to see if we were able to measure that. And the conclusion from that story is that, sorry for this huge graph, we are not going to go through everything. It works well. I mean, when you fly with a drone-based GPR over snowpack, that's what you see on the left side of this slide. I mean, it's easy to see the spatial variation in the snow property by calculating the permittivity. It works well. Really good correlation with manual snow pits that we dig every week also. So when we make stats about that and you compare with manual measurements, we discovered that, yeah, you know what? In dry condition, it works really well. In wet condition, it's more complicated than we thought. And the result we had are still, shows that there's still some work to do. So now we are testing other combination, of studying the magnitude, but also the frequency, and trying to combine those to have better information. But there's still some job to do to have tools that really you fly over a snowpack and you know exactly what the water content and what the distribution of the water in your snowpack. So there's still some work to do. But fortunately, otherwise we will lose our job. And yeah, and last things, I still have 1 minute, I think. So last example I want to show, it's also an application we had in similar environment, but it's not about snow, it's about frozen ground. Seasonal frozen ground is very important question because it creates permeability, or it affects the permeability of your soil during the winter and the spring, which means a huge impact on recharging the groundwater. So here we flew over in a field every week during 8 weeks over following the same transect as much as possible, and trying to see what the evolution of the frozen ground. So it was not huge. Frozen ground was 30-40 centimeters. So we had all the tools to help us to quantify, to evaluate the real thickness. And here again works really well, even if again, when it's wet, the interpretation is really, really difficult. But the papers that submitted and should, I hope, be published soon, allowed us to show that, you know what, yes, the frozen ground is quite homogeneous during the winter. So when you keep cold condition, I mean, there's not so much happens. It's a bit boring. But when it starts melting, it melts by patches, and you have the creation of preferential pathway for the water. And this one makes that the idea of a frozen ground that until 15th of March, nothing happened. Then past 15th of March, you have soils that allow the water to go through is probably not that accurate because it happened by patches. So you have a transition period during which one your soil, the condition, the ice condition, the frost condition in the ground is in fact extremely heterogeneous, making that there are some areas where you have a permeable soil and some where you have not. So here again, good application. I think we did it with the 500, and yeah, we were surprisingly happy with what we have been able to achieve with that. I think my next slide is, yeah, thank you. And if we have questions, we can go on.
Thank you, Michel. Thank you. Question from Bastian. How do you estimate permittivity in dry snow?
Oh, it's just, you know, taking the TWT. So the GPR gives you a time, the time for the signal to go through a layer in the two-way. Go one way, reflect on the next one, and go back. So, and there is a direct link between the velocity of this wave and the permittivity of the milieu that you cross. So you just need to add the distance measurement, and automatically you get the velocity, and then you get the permittivity with a single thing. So it's why also I didn't mention it, but why did we make some snow survey with photogrammetry? It was to have this idea of having the thickness of your snow layers, and by adding that information to the TWT, we just extracted permittivity.
Thank you for this response. Yes, as Sabine just written in chat, please use Q&A session. Question, Michel, you have like almost all sensors that can be imagined, but if you had a magic wand or anything, what would be the next sensor you want to be drone mounted?
This is a good question. In fact, there is one sensor I would like to see on the market is EM, electromagnetic. So it's like the magnetometry that we have seen with Jamie, but then you don't only measure the natural signal. You just create a signal and you measure the response. So EM, for that you need two, a bit like a GPR. You have one emitter, one receptor. The problem that to go deeper with EM, you need to have the emitter and the receptor far away. So far, this method is limited to extremely shallow investigations, probably 1 or 2 meters, because if both are the same drone, I mean, when it's more than 2 meters long, I mean, there's no way it can do more. I know that there are now a lot of development with drone fleets or UAV fleets, you know, having coordinated flights. So my dream that I would test there would be really to have the emitter and the receptor on 2 different drones flying, I don't know, 10, 15 meters apart, synchronized. And then I would have a second drone-based geophysical method that I could use to help the interpretation of the GPR. And something I didn't mention also about the interest of drones and drone-based GPR in where we work. In glaciology or hydroglaciology, most of the traditional method have the problem that there is a kind of bias in the results we have, because we have to make measurements where it's safe to go. You know, losing a student in the summer, it's not good. So you have to, and the drone allow you to go and measure in areas where nobody would go. You know, and that's why, you know, you have this unique data set. The only thing that when you cannot go, you cannot apply all the methods that would help you for the interpretation. So that's why EM, combining EM and drone-based GPR on accumulation areas of glaciers, for example, I think it would be a game changer in our field.
Got it. Thank you. Jamie, what about you? You also have quite a broad experience with drone-based sensors and payloads.
So for me, it's a sensor that exists and might have access to is using the radiation detectors to do soil moisture mapping to see if how those show up on how those work on archaeological sites. We might be able to try that and see how it works. I just have to try to talk ODH into letting me use their radiation detectors. So hopefully that's something we can actually try.
Good question from me, basically. We all know that sometimes it's not that easy to get funding or grants for your next research project. How do you think drones and all these new technologies, do they help to secure funding, or do they don't make any difference, so to say, or otherwise, or vice versa, it's more complicated? What is your experience? Michel, Tyler, as you people from academia, and what do you think?
It's a good question. It's an extremely good question. I think if we have the answer, then we can, we would be, we would have much more equipment, and it's not easy to know what make a demand that's going to bring something. In our case, we focus a lot on the finality, why we need that and why we can't do our research, or we cannot push the research as far as we want without those techniques. And I think that what has been successful so far. Now, when the funding agencies, at least some of them, they like to have novelties. So it's extremely difficult to have an equipment in the lab, that is used by most of the prof to measure, I don't know, ions, something like that, and then it breaks down. And to find the money to get it replaced, at least in our case, it's extremely difficult. It's easier if you show that, wow, I'm going to, test a new technology, and this will serve the entire country. So yes, it helps for the novelty, but the problem with the technologies that go so fast is that at a certain point also the agencies have difficulties to follow the really fast evolution. So that's I mean, what would be ideal, I think, is to have the sensor evolving a lot. But then if we have a slowdown in commercial drone development, to show that we showed our good Matrice M600 Pro, which was 5 years ago, that was wow, everybody needs to have that. Now when you fly it, I was looking at Jamie's slides and he has a 600. I mean, it goes so fast, but this drone is fantastic. But when you say, oh, we don't support DJI, say we don't support M600 anymore, it means that for us, we have to ask money for new drones without providing a new service, or without exploring anything new in science with new sensors, something like that. So I think for the sensors, for the GPR, thing like that, it's really helps. The problem with the drone, that's to keep updated and to have always the latest drone, it's a problem for academia.
I'll maybe just add on to that as well. From the college standpoint, we're more on applied research. So we're taking, technology with high technology, like readiness levels, and integrating it into existing workflows. I think there's a lot of grants currently, at least in Canada, that are specifically ready, and they want fast-paced solutions to problems that already exist. I know there's quite a few for exploratory stuff as well, but from the college level, those are the types of grants we look at, and there's quite a few out there that we can tap into. Again, we have IdeaWorks, which is our whole area that's devoted to finding those grants and such. So I'm by no means an expert, but what I've found is if you can form a partnership with an existing company or an existing organization to help tackle a problem that they have now, those are where grants seem to be getting devoted right now. And to fund Canadian innovation. So.
Thank you. And the last question for today, because we ran out of time, Pete. How does the drone industry can help you? What can we do better, or what can we what can we do better? This question is to all of you.
So maybe, Jamie.
Go ahead.
Okay, I was just gonna say, you guys seem to listen to feedback a lot. One of the things I wanted was a multi-beam sensor on a drone. I know that was gonna be a hard problem to solve for like the tilt correction on that. And I see Alexi's already got one cooking up already. So really just getting it in people's hands so that you can get user feedback is probably gonna be the best thing. With the city of Hamilton, we saw it as well. Getting the most amount of ponds done really unravels all the insights you can get on how that technology is gonna actually be used in the field with the technicians that are going to be using it. So really using academia as a way to product test is usually a great way to fastly evolve your products.
Thank you, Tyler. And by the way, this multi-beam mecha sounder should be ready for pre-order quite soon. Michel, what would you say?
Yeah, I think you know, the example I gave with LF and the need to use it in the bistatic mode for CMP, I think was great. It's a great story about, you know, how cooperation can really help both parties, because I think probably we are developing at least a new idea, a new concept for SPH, and for us, I mean, it makes that we have been able to use the LF in a condition where probably many other researchers or users may face, but in our case, we cannot go there and try things that do not work. So, you know, we could try ourselves to develop things, but why do we work with professional and companies? Because we are not specialists in the sensor, we are not specialists in drones. We just want to be users. And I think that, you know, knowing that company can help you to find solution and you know, tailor a bit the product to make sure that it applies to those conditions. I think it's very interesting. So I hope we'll have other opportunities, maybe with the EM we just talked about. So if you want to develop it and you need to test it in harsh condition, we are volunteer.
We have some ideas. A little
Cool.
spoiler. Jamie, you are the one to wrap up this conversation and this question.
I would say for us, it's so Ohio, we've seen the legislation that DJI is going to be banned. I wouldn't be surprised if all DJIs were banned in the US at some point, and it's the ease of use of non-DJI stuff. DJI drones and your guys' software specifically work so well together. And then you get into the non-DJI stuff, and it's kind of you never exactly know what you're going to get out of, you know, the software and how they're all using it, and just that ease of use with the non-DJI stuff, I think will go a long ways.
Thank you. That's a great feedback. This is something we should work more on. Okay, it's 17 minutes past 6 p.m. and that means that we have to wrap up now. Thank you everyone for your stories, for your feedback, for your ideas, and I hope that all listeners learned something new today and they have new ideas how to implement drones in their research. And I hope to talk with you all quite soon. It was a pleasure having you here.
Thanks, everyone.
Thank you very much for the invitation, and thanks
Yeah,
for
thank you.
everybody for sharing also their experience. It's very interesting also as a attendee. Bye.
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 Thank you so much. Bye.